This is about cold plate cool liquid rack guideline update. So this basically we're introducing 3 different coolant, and the guideline will be tried to publish by the end of the year. Agenda is, well, this work stream actually started back in 2021. Sean actually helped start the discussion about starting a work stream about white paper for coolant. So at that time, we actually published 2 papers based on the water and the PG25. And last year, we actually, since there's a more demand on liquid cooling, so we actually add the two-phase dielectric coolant to this discussion. So if you want to look at the previous guideline, you can actually look up the wiki page on our OCP website and also have the link. If you have the slide after the conference, you can click the link, directly get the paper, and you don't have to worry about losing the track. So, and you can use the QR code to find all the connection as well. So the key all about discussion is based on the liquid cool rack. So this is a core discussion of our topic. So we're talking about CDU coolant and the cold plate connected to the CDU and what kind of coolant need to be used. Could be a water-based, could be PG25 and or two-phase dielectric coolant. And it's a heat transfer different, so you can choose and pick depend on the system demand, what kind of coolant you want to use. And this is a general discussion about how 3 different coolant is different. So basically, thermal performance, the best is dielectric fluid. Maintenance schedule, the highest is the treated water, because treated water has the best heat transfer compared to PG25, but the treated water tend to have a biofouling. So there's a lot of maintenance in the beginning. If you keep it clean, it can run for a long time. But if you start having a biofouling issue, you have to keep adding biocide, try to mitigate the issue. So that's the biggest concern. So sometimes people will try to switch from treated water to PG25 if their thermal performance can allow that. Then for electric conductivity, the best performance is dielectric fluid. Environmental concern, there's PFAS for the dielectric fluid, and glycol in the discharge for PG25. There's some municipality has the issue about discharging it. So for treated water, there's no issue at all. The cost is relatively low for treated water, and PG25 for dielectric is a little bit higher. So just an overview, we had two papers published in 2022, and we'll have tried to wrap up the new document by the end of the year. And you're welcome to join our meeting. We have meeting every 2 weeks on Monday. So the next meeting will be next Monday around 8 a.m. Pacific time. So here comes my topic is based on water-based coolant. So basically this revision from previous document will cover basically the guideline, safety, and how you choose the coolant, the consideration of the coolant, the property on material compatibility, and what you need to pay attention when you start it up. So startup is the most important. A lot of issue, because when they ship the equipment to the location, it could be pre-tested with some coolant left in there. If they left without any care, after 6 months, there will be bacteria growing inside the liquid. So that's the biggest headache when they try to start it up. So once it's started up, you check the weekly on the coolant quality, and if it's everything stable, you can do monthly check. And then after that, you just maintain the azo above 1,000 ppm for copper protection. For treated water, we recommend using a 1 micron side stream filter to just keep the biofouling to minimum. And that's the biggest concern. And for our discussion, we actually come up with a new suggestion for vendor. They should have a pH sensor as an inline, so you can actually monitor the pH shift as an indication of biofouling start happening. So this is basically what we try to cover for treated water. And I will turn over to Keegan for PG-25.
Perfect, thank you. Just click the right button. Yep. Okay, hi everybody. My name's Keegan Yaroch. I'm from Dow Chemical, and I'm co-leading the cold plate coolants workstream with Philip and Shahar, but my focus is on propylene glycol-based single-phase coolants. So today, I'm basically just gonna go over some of the changes that we made from the 2022 document, and then review some of the highlights. So it's definitely not all that's included in the document, but it's definitely the key parts of the document. Before I begin, I do want to thank David Miller, Third Coast Indorama, for all his help in shaping this document, so thank you very much. Okay, so what can you expect for typical properties of a PG-based coolant? Biggest thing is it's going to contain greater than 25% propylene glycol by volume. The reason that this is important is because anything 25% and greater is considered biostatic, meaning there would be very minimal risk of biocontamination. Next, PG-based fluids should be low toxicity, non-flammable. You should achieve freeze points of 15 degrees Fahrenheit or lower, depending on the concentration you use. And then they should be industrial inhibited. So this means that they contain additives and inhibitors that are going to protect, most importantly, the metals in the system, but also prevent any issues with drops in pH and stuff like that. So last but not least, you would expect a long fluid lifetime from a PG-based fluid, an inhibited PG-based fluid, with minimal intervention necessary. So you're not going to have to make adjustments to it routinely. It's going to be pretty straightforward maintenance. Okay, for wetted materials, this is obviously a hot topic. Minimal changes were made from the 2022 document. There's just so many materials that are being used, it's nearly impossible to address them all, but we did want to kind of give guidance on what can be done or best practices for ensuring wetted material compatibility. So it's important to note that the wetted material list is conservative, slightly conservative. It doesn't contain everything that can be used, but it's a good starting point. Ultimately, you should ensure compatibility of all your metals in the system, all your elastomers, plastics, sealants prior to use. And that guidance can be given by the heat transfer fluid manufacturer, the component manufacturer, or by doing your own testing. Okay, so what do you do if a material is not on the list? There's some ASTM methods that we would recommend. The first is ASTM D8040. That's basically an exposure corrosion test. So you would take metal coupons, immerse them in the heat transfer fluid of choice at your chosen concentration. You'd add corrosive salts, and you'd have constant air bubbling through it, kind of to accelerate the corrosion if there were any potential corrosion risks. And then at the end of testing, you would take the weight loss and determine corrosion rate. And then from there, you can determine if the fluid or the metal is acceptable for use. So another thing to point out on this is it's a good first pass. It doesn't take the place of long-term testing in a system, but it is a good starting point. For plastics and elastomers, there's two more tests. ASTM D638 and 543, and then D412 and D471. Those are exposure tests where you would immerse coupons of the plastic or elastomer in the heat transfer fluid, exposed for 2 to 6 weeks at your usage temperature, or slightly higher if you wanted to do a worst case scenario. And after testing, you would, before and after testing, you would weigh the materials. You would do volume measurements, tensile strength, hardness, and then calculate the change over the exposure length, and determine if the material is suitable for use. Important to note here is the heat transfer fluid manufacturers won't have all the answers. A lot of times you need to consult the component manufacturer because they all have different guidance on what's acceptable. A prime example is EPDM hosing. So one manufacturer may say 10% less swelling is acceptable, and another might say 15% or less is acceptable. I don't know all those things, so I always consult the manufacturer when possible. Some of it has to do with the composition of the elastomer or plastic or the curing process, so there's, best to consult the manufacturer of the component. Cleaning, this is another hot topic. So in our 2022 guideline, we were pretty conservative with some of the guidance we gave on cleaning and what could be used to flush the system. That was done because we didn't want to risk over diluting the fluid, since when you're operating at 25%, you're kind of at the lower range of where we would recommend. We realize that's not feasible now. Obviously, for larger loops, you know, you have to be able to flush with a water-based solution. So the document gives a couple different options for flushing, either treated water, surfactants, biocides, what have you. So there's multiple, you know, there's an expansion upon our previous guidance. The takeaway from this section would be that if you use a water-based cleaner, you must ensure that you get it all back out, particularly if you have biocides or surfactants in the flush fluid, which can interfere with the heat transfer fluid, could cause foaming and other issues. So that's the first thing. If you do flush with water, you also need to verify what the glycol concentration is after fill and after you've had adequate mixing. This can be done with a refractometer on site relatively easily, but if you're low, you should also have a plan in place to increase the concentration right then and there. So have a more concentrated fluid on hand or something, just a plan so you ensure that when you're starting that you have 25% or greater glycol. Okay, fluid monitoring and maintenance. This is one of my favorite topics. There's a lot of questions we get about what you should do to maintain the integrity of the heat transfer fluid. We do recommend two types of analysis. One would be a comprehensive annual analysis. That's often done by the heat transfer fluid manufacturer or a qualified third-party lab. It's best that the third-party lab is working with the heat transfer fluid manufacturer so they can provide adequate guidance. But the goal of that analysis is to paint an overall picture of the fluid health. So things we would look for would be glycol concentration, fluid pH, reserve alkalinity, contaminants, scale promoters, corrosives, metals in solution. So really a very robust analysis. And the goal of that is to tell you one of three things. So A, the fluid is suitable for continued use. You don't need to do anything. B, there's something off and you need to modify, maybe add an inhibitor or a booster. Or C, it just needs to be replaced altogether. The next type of analysis would be on-site analysis. It's not a requirement, but it is good practice. This would just be a more straightforward analysis and doing glycol concentration via refractive index, fluid pH via a pH probe or test strips, or reserve alkalinity, things like that. So relatively straightforward, easy for the data center operator to do themselves. Can be done on whatever frequency you like, biannual, quarterly, but it's definitely good practice. And I've included a picture of the refractometer. I recommend digital refractometers that indicate units of refractive index are the most reliable, in my opinion. But this MISCO unit is really great, so I've had a lot of success with that. And with that, I will hand it off to Shahar.
Thank you very much. Good morning. My name is Shahar Belkin, and I'm the EVP product for Zutacore. And I want to share with you a little bit of the things we've learned in the past years of experience with the dielectric liquids. So a little bit about the two-phase liquid. It's a bit different than PG25 because you can select the right liquid, meaning you have properties for the liquid that would fit or not fit the object you want to use. For example, when you want to cool CPUs today, you want to have something that boils around 51 degrees. So you'll use a liquid like SF33 that boils at 33. Or if you want to need to cool AI chips that need lower temperature, you'll select another liquid like the 1224 YD that boils at 14 degrees. So there's a lot of selections, but I want to try to make sense in all of that. So first of all, you'll look at the safety of the liquid, meaning are you willing to have any flammability in it? Flammability, the answer is not constantly no flammability. I did hear answers say we can use some flammability if we use the right fire suppression in our data center. So it's not a one answer, but look at flammability. A lot of these liquids are non-flammable at all, so it's very, very safe. Another hand is toxicity. Why do you want toxicity? Nobody drinks it, but you have people treating it. It may leak and you have some vapor in the air, so you need to have, I would say, low to no toxicity at all if you're selecting a liquid to work in a data center. The next part will be seamlessly, but it's sustainability. And in sustainability, you would want, of course, a low global warming potential. There's liquids that have been used for air conditioning with thousands in the global warming potential figures, but now the new liquids coming out are lower than 20, even 5, 2, 1. So look at the minimum, so you won't have affecting the global warming. And then ozone depletion should be around 0 in any one of the new liquids coming out. And the last figure that has now been on the news in the last 2 years is PFAS. So PFAS manufacturers have been reducing it, but the news is that next year we'll see liquids that will be 0 or PFAS-free, as it's called, and that is coming out. And this is a very important topic because some of the data centers are not willing to use anything with PFAS in it. So that's a figure that is very important. And then when you finish all these, you go to the real functionality of the liquid. So I said boiling point should be a very important point to look at. So you have boiling points from -11 to +40, and you'll have to decide which one of them is the right one for you. Meaning boiling point is not the real boiling point because you're actually using it with a little bit higher pressure, like 1 bar, but you can select it, but you don't want to use very high pressure systems. So you use a boiling point similar to the one you're actually going to use. The next part is called dielectric liquid or a non-conductive liquid. Seems that it's not really important. It's very, very important because a leak there would prevent anything from happening. And I want to show you something because just talking about it is something else, saying dielectric. But if you use a liquid that is dielectric, it means that it's exactly safe to electronics. I want to show something for a second. And I hope the presentation will continue. And then a freeze temperature. Freeze temperature doesn't really matter in a data center, but if you have such a low freeze temperature on these liquids, you can actually ship a full loaded rack with liquid inside without having to drain it and refill it in a data center, so that makes it important. And then we move to the next topic of material compatibility. And that is a little bit more complicated in these liquids because material compatibility is different per liquid. Each one of the liquids attacks different parameters or different materials in the sealing, in the tubing. So every material you want to use, you'll have to retest for material compatibility. And when we talk about material compatibility, is testing and making sure that when you're using it, for example, a seal, there's no weight change, the stiffness doesn't change of the O-rings, volume doesn't change. Those are the tests we're doing. And then another test is permeability. It could be that the sealing and everything looks like nothing has changed, but you'll be losing liquid if you use the wrong materials for the sealings of the system. So every material, every liquid has different compatibility to different materials, but special attention will be to the gaskets and to the flexible parts and the components like tubing. In general, most metals and hard plastic don't have any material compatibility issues, and it's not like PG or water. You do not have to check aluminum, copper, any one of them, and they can work together without any problem because of the dielectric features, so you don't have any erosion between components. What are the recommended testing? So if we talk about performance, all components like pumps, cold plates, of course, valves, solenoid, that are moving, that are using in the liquid because of material compatibility, but not all. These liquids also change in velocity or viscosity, so a pump has to be fitted to fit those kind of liquids. When we talk about material compatibility, we want to recommend some tests. One of the tests is a Soxhlet test, meaning that this is what we call accelerated aging. 72 hours in a Soxhlet test will be compatible to a 3 or 4 months work in a system. But at the same time, we recommend a long-term full system leak test to see that the system is completely sealed. And we will recommend testing permeability so you do not lose liquid from the system from any of the sealings or the tubing. Just on the mechanical design consideration, I would say that it's very similar to the water, but making sure here you have a filling, a purge, and a draining ports in any one of the system. Draining is very important if you want to decommission it, but a purge is something that is needed from time to time in these kind of systems. It's not only topping on. When you replace servers, you take some of the liquid with the server and you bring some air in, and that air needs to be released from the system in a process called purge. Not very complicated, but needs to be able to be done. And last part in the mechanical is filtration. Filter here is not as important as in water or PG because there's no biological growth, no corrosion, no erosion in these systems. So we recommend like 100 micron, and that's mainly to protect the pumps and not anything else in the system. Thank you very much.
Thank you, Shahar, and thanks for the demo. There's no damage on the laptop. So last one, we'll call for action. We'll welcome everybody to come to our workstream meeting. So as I mentioned, next Monday, if you want to join, you can actually scan the QR code and join our mail list, and we'll send you the meeting invite automatically. And with that, I'll be open to any question that you might have. David?
Thank you, all three of you. Excellent presentations. So, question for Shahar with regard to the two-phase fluid. Is this working? Closer. How's that? Yes, okay. With regard to the two-phase fluids, and with such a low boiling point of around 18 to 40 degrees centigrade, when you fill it and you want to air purge it, if the system is trying to evaporate whenever you open it up to do the air purge, how do you get the air out is one question. And a related question also is if during the system operation, how do you determine if it's leaking, if everything evaporates instantly? Is there a mechanism for monitoring leak detection, and how does that work?
Good questions. The purge part, you do need a purge unit, like the unit we saw from Meta, but much smaller. So what you do is you get all the vapor and air combined together out of the system, out of the buffer area, and then you purge it, meaning you compress it and see that the air that is not compressed can be released, and anything that could be compressed turns into liquid, and you pump it back in. So that's a separation unit. That's one part. The second question was?
Oh, okay. The second question is with regard to leak detection.
Okay.
So if you do have a leak, a seal's leaking, and it evaporates instantly, how do you know?
Yeah, again, a good question, because leaking cannot be done by water. There is hardly a way to catch that liquid because it really evaporates. The way it is, it's monitoring very closely the buffer level inside the system. There's a buffer inside every CDU, and you see if you're losing liquid, you'll see the buffer level going down. So that's one way of doing it. Another thing, there is sniffers that could be installed in the RECs that sniff the vapors, and that's another way to do it, and a very quickly way to do it. The one good thing about it is a leak never damages the servers themselves.
Okay, thank you. And going back to the first part where you're doing the air purge, so when you pressurize the two-phase fluid in, I assume it liquefies, and then you can see the air in the headspace, so you know when it's liquid full. Is that the case?
Well, yes. When you compress it, all the compressed vapor turns into liquid, so you can pump it out, and anything that left in that container that you compressed is uncompressible or other air. Not always air. It could be anything else, but it's an uncompressible thing.
Okay, thank you.
All right, we're out of time. Thanks, everyone.